Thank you for coming out tonight. Welcome to Metis. I had mentioned that we were going to live stream this event, but it is currently not working. We're having some technical difficulties, but we are recording the event, so it will be available afterwards, and it will be available for our online community. So if you'd like to refer back to it, we'll have that for you. Thanks. But real quick, before we get started, show of hands, can you tell me how many people here have heard of Metis? Great, so a number of people in the room tonight. I'm just going to do a quick introduction of what Metis is, who we are. First of all, my name is Nathan. I'm the program manager here at Metis in Chicago. At Metis, we are a data science educator. So we started in 2014 in New York City. We expanded out to San Francisco. We're currently in Chicago and also in Seattle. How are we a data science educator? We do it in 4 ways. We have our main way, which is our 3-month intensive boot camp. So that's done on-site here in Chicago and then in our other 3 cities. It's 3 months on-site intensive, Monday through Friday, 9:30 in the morning to 6 p.m. At night with 2 senior data scientists. You're working on 5 project deliverables. So that's one way we do it. That also comes with career services as well and a number of other things. If you have any further questions, I'll be around after the event to talk to you about that. We also have our professional development courses. Like Drew taught earlier this year, we have our Intro to Data Science course that we have on campus, so those are done on our campuses as well. We have our live online courses. These are a number of courses that we have done with our senior data scientists based across the country, and they're 100% live, 100% online. And lastly, we do a lot of corporate training. We do corporate training throughout Chicago, throughout the United States, and the world. So if you were to be interested in any of these points, I'll be around after the show, after the meetup, so I can speak to you then. Okay? I think without any further ado, I'm gonna. Okay.
Thanks, Nathan. Thanks, Metis. So welcome to December meeting of PyData Chicago. I just wanted to touch on a couple meetup things that are coming up. So, like I said, this is we're gonna have 3 more meetups here at Metis, and then we're scouting out another location. We have something lined up. Once we finalize that, we'll share it with everybody so y'all know what's going on there. But our last one here will be in February, the first Monday of February. And on that note, we would love it if somebody here thought it would be nice to present in February. We have a presentation lined up for next January. I think it's going to be on the 2nd annual Data Science Bowl from Kaggle, looking at MRI studies to try to predict heart diseases. So that'll be fun, but we need somebody for February. So it's a great way to kind of get up there and get your name out there and to share in this education that we kind of have going on in the meetup culture here in Chicago. So if anybody wants to come potentially present, just come see one of us tomorrow. So yeah, and then the last thing I want to do is just introduce Drew Froston. He's given the presentation today. Drew is a physicist turned data science. His physics PhD thesis was looking at defining the limits of being able to detect dark matter using a bubble chamber buried deep under the ground. And if that wasn't impressive enough, he then proceeded to accelerate in the data science community, starting as an insight analyst at Grubhub, and then moving on to be a data scientist at H2O, and then ultimately, within 3 or 4 years, becoming the lead data scientist at Spot Hero, where he built a team to deliver supply-demand forecasting, price elasticity models, a lot of cool stuff. And now, he recently started his own company, Automaton Data, where he is acting as a data consultant on all things data, data science, data engineering, data architecture. So if you're looking for a strong consultant and you want to get some advice, come see him afterwards. So without further ado, Drew is going to be talking about interrupted time series experiments and how to do those.
And what that even means. Thanks, everybody. When he says, you know, if you want to talk in February or whatever, I just wanted to learn this topic, so I put it up on the calendar that I was going to give a talk today, and then I learned the topic, kind of. So it's a good way to kind of force yourself to do things that you wouldn't otherwise do. So that's nice. There. So I'm going to talk about interrupted time series experiments in Python. Other sorts of names that tend to be used for something like this is residual discontinuity design, RDD, which specifically doesn't have to do with time series. But basically it's just the concept of, usually when you do A/B tests or anything like that, you might hold aside a part of the population to be a control and a part of the population to be like an experiment group that you give some sort of variant to. And it's nice that way because you can actually select out your population so they're like statistically significant, and then you kind of look for maybe a difference in conversion rate or something if I give them a green button instead of a blue button or something like that. There are plenty of examples where that model doesn't exactly work. And this is the reason I actually wanted to do this, was because when I was at Spot Hero, I was trying to do a model for our radio advertising. And so if there is a radio ad, that radio ad, I can't like select which users that radio ad goes to. It's either on or it's off, right? And so to be able to actually tell the difference between when that radio ad is on and what our transactions look like, and when that radio ad was off and what our transactions look like, would be an example of an interrupted time series experiment. So you have a time series, you're trying to predict it, forecast it, and understand what's going on, and then you kind of change things throughout and like look at what happens at that change. Right? So it's a lot less controlled, it's a lot more complicated than normal A/B testing or anything like that, and so that's ultimately why I wanted to talk on this. I still have the POCO idea of actually how to do this really, really well, so you're going to come along with me as we learn too. I am Drew. This is my wife and kiddos. I was mentioning earlier that she's terrified of Alexa. I don't know why. So I have started a company to try to like do contracting work here in Chicago. Prior to that, I was at Spot Hero most recently, also at Grubhub, and then a stint at another startup that I just don't like mentioning. And then also was at the University of Chicago. The idea with experiment, and I love this meme. It's super old and everybody's seen it, and every time I see it I laugh. It's almost as funny as the hello, yes, this is dog. That one, like literally I laugh every time I see it. But when you're running experiments, sometimes they're quite hard, and in this particular case that we're going to talk about, they're actually, you know what? Before I even start about talking about this stuff, how many people in here are familiar with doing like time series analysis? Like the word ARIMA means something to you or something like that, right? How many do that on a regular basis at work as well? So, okay, cool. And if I say the word like Poisson distribution, how familiar? Everybody's kind of cool with that, not cool with that? Okay, cool. I'm just trying to get a little baseline. Okay, so some experiments are straightforward. I don't know why this clip art decided the shift key needed to be A/B testing, but you just hit the A/B testing key and you're good. This is actually an example of something that kind of looks hard, maybe, but is actually fairly straightforward because you can select out these different populations, A and B, and you can actually look at how the variation hits on each one differently, and you could look at basically what's the probability that that the signal on B is greater than the signal on A, and it's either you use some sort of classical statistics or you use some sort of Bayesian methods to figure out like to 95% confidence or whatever you want to do. In fact, PB has received some sort of lift versus PA, and that sort of stuff is actually pretty straightforward. But then there's sometimes where doing time series are really convoluted and difficult, or doing experiments. If you can imagine, as I was talking about earlier, you have like a radio ad that kicks on here. So observed is blue, green is forecast here, and so you can see that this wonderful little ARIMA model maps out this same shape, and it continues that going forward. The error bars kind of expand as time goes on, as you would kind of hope that that would. But in the same regard, you see that just because this is at the beginning of 2013, and for whatever reason, observed like immediately has a step function sort of difference, right? But that has nothing to do with anything in this experiment. That was literally just, oh, I plotted it here. Actually, I didn't. This is Tom Augsburger, who's one of the Pandas contributors, who's really great. If you ever get a chance to hear him talk, he lives in Des Moines, but he comes into Chicago every once in a while. Really good. There wasn't anything that happened here. He didn't choose this date for any particular reason, but you could see what would happen if I happened to launch an ad campaign on this particular day, and all of a sudden the time series does that. Do I attribute that to the lift of my ad campaign? Do I not attribute that to the lift of my ad campaign? In fact, given that other than this maybe one point right there, everything is within like a 95% confidence band, that's actually not even a bad forecast here, and doesn't look like anything's really an outlier, right? So those are the kinds of things you have to take into account when we're talking about like an interrupted time series. So that's what's complicated with this, and this is what it kind of looks like when people, if people were to do something. This is kind of a good example where you have a bunch of different experiments. I don't even know what this is on. It's a perspective controlled trial of electronic hand hygiene reminder system. So if it chimes, you got some good hygiene. If it chimes and displays, you got some really good hygiene. I don't know what washout means, but you can see that like it's pretty clear that there's some dots there and there's some dots there, and I would guess there's a discontinuity there. What's best is if I actually know what this gray line is right here, because then I can say, hey, is there anything different on this side versus that side? Really, really hard time series analysis like this would be that I don't actually know when this happens, and if that's the case, you have to kind of detect where shifts happen and also detect like what the change in the shift is. And so what you might do here is you might like fit a curve here and say, oh, this curve has a slope and an intercept of this. This has a slope and an intercept of that. Those two curves are different to some degree of certainty or something like that. That would be an example of what's called RDD, which I'll talk about briefly in a second here. But then you have these other examples like this, which ignore the red line. Is there any difference in that time series? There's like no freaking way, right? Like, for one, this is like, 12 whatever observations. I guarantee you that they came up with some sort of like, just some sort of p-value, I don't know, whatever. That they decided that this was actually a difference, and the difference was maybe like a 2% drop or whatever else, right? No. So, interrupted time series, they're actually called quasi-experiments, and I joked about it being that they're shaky because they're called quasi-experiments. This actually has a meaning. I don't really remember the meaning to it, but it has something to do with like controls and everything that you would think of with the scientific method. And as I said, they're related to this RDD, regression discontinuity, which is basically, this would be an example where usually in RDD you kind of measure some sort of polynomial fit right here, and then you look for differences in those. But oftentimes they're not for some sort of continuous variable like time would be. So I don't actually have an example right now, but like suppose there was some sort of distribution of age, right? And so it's just this nice little Gaussian distribution. And at 35 years old, it's nice and continuous or whatever. But suppose I were to say, for people over 35 years old, you now have to pay some additional amount of tax, or create something. But that's not like a time series where it's this continual variable. I can sample all around that cutoff point of 35 and find thousands of people under 35, thousands of people over 35, and actually get a really good idea of what the distribution looks like on either side of that. And that's the real core of what RDD would be. And so it kind of requires that near the cutoff point, you have randomly assigned or like randomly sort of distributed data points around it for it to actually hold, and that doesn't exactly hold in time series land. So I only mention this because somebody mentioned to me like, oh, you mean RDD? Like, oh, I'm surprised you don't know about that. So so I figured out why it was different, in fact. So I found this book, so I took a couple pictures every once in a while. But an example of what an interrupted time series would be is that you fit an ARIMA model, let's say, and you add in some sort of effect size, let's say. So in this case you have, and again, like, oh, look at that time series, right? And I'm not very pleased with this book because there are a lot of times where it finds some really significant values for the effect size that, just by my eyeball, I don't believe it, so that's usually how I do things. The time series here, I know this is a little bit small, but it's basically y as a function of t goes to some constant plus some sort of Gaussian distributed noise plus some effect size times this it, which is basically like a step function. So W0 it when t is less than that is 0 wt, or W0 or omega 0 it up here is omega 0. And so what you do then is you can actually fit, just like you would any sort of linear regression kind of thing, you can fit this curve to the data and find the parameter, the best fit parameters, and then determine if this omega parameter is in fact significant, right? And so then he's got some t-tests here, and he says, yep, that's significant. It's a 1%, you know, shift downwards, and I mean that's a small number. But that's how you would do that. Now, I don't know if you're, well, yeah, I'll get to, yeah, I don't know if you guys are like me, guys and girls. I'm really trying to break my Midwestern you guys thing, and I can't do it. Anyhow, y'all, I don't know if y'all are like me, but when it comes to ARIMA, usually I just take a time series. I find my little ARIMA function in like stats models or something like that, and I just throw the time series at it and poke around at different choices of P, D, and Q or whatever until something makes sense and kind of looks okay. If somebody were to tell me, oh yeah, just add like a different term to it and then just fit that instead of like your standard ARIMA, I'd be like, oh, never mind, I'm out. And so that's been one really awesome thing about going through this whole process for me is that turns out ARIMA is not really complicated. And it kind of like sticks in your head once you kind of get an idea of how it works. So, and then you can kind of engineer your own sort of ARIMA fit if you're so inclined. And as I said, with like something like an RDD, another idea is that you could fit curves at the discontinuity. So this kind of looks like a spline maybe, or some sort of, I would personally just put a line there. And then you can see with the dots here that there's some sort of other line here and then maybe another line there. And so you could imagine that what this would be is that there's an effect size of some level, but then it decays away, right? So that like everybody freaks out and then, oh, never mind, and then they go back to normal, right? And so you can get complicated where you're not just looking for like the effect size omega 0, but maybe you're looking for like what is the functional form for which that effect size turns on or decays away or whatever else. So there could be multiple parameters that you actually have to fit for this like dip term here. So so that's the overall structure of like what we're gonna do. So to do that, I wanted to simulate some data. So namely because I don't work at Spot here anymore and I can't just like grab the data off the database anymore. So so if I say homogeneous or homogeneous Poisson point process, what that means is basically if I take a, so it has some sort of parameter lambda, and if you're familiar, like a Poisson distribution has like one parameter that kind of defines it. The mean and the variance of that distribution are both lambda, right? So it's kind of like a normal distribution, but a normal distribution is described by a mu and a sigma, so like where it's centered and how spread out it is. Poisson only has this one, and it turns out that mu equals sigma equals lambda, right? And then from that you can derive all the rest of the characteristics of it. But what a Poisson process does is it basically is what you would use to model like discrete events in time. Like people would use them for like bus arrivals, right? There are some definitions to them, like there's independent increments. So if lambda is 5, that's not to say that 5 minutes is my expected value. No, it is. This is what mu means. So if lambda were equal to 5 minutes, let's say, my expectation value of when a bus is going to arrive is 5 minutes. If a bus hasn't arrived for 15 minutes, my expectation value is 5 minutes. It does not care about the past. It's always 5 minutes. It's a sort of constant number. It does not care about like some sort of current, like lag or anything like that. That's what it means about like independent increments. If a whole bunch happen at once, sure, maybe my Poisson changed in frequency or something like that, but mu is 5 minutes. Lambda equals mu equals 5 minutes. So a Poisson point process that is homogeneous means that lambda is fixed in time, which is the easy world. And that means if I pick like a time t, the expectation value of how many events that should arrive in that time t is equal to lambda times t. Okay, so, but the other thing that is true of Poisson point processes, and I know this is small and I just copied off of Wikipedia, the time differences between events is actually distributed as an exponential with exponential factor 1 over lambda. Okay, so the distribution of events in time is Poisson distributed. If I take delta t between each of the events, that should be exponential distributed. Okay, also defined only by one parameter, lambda. Okay, so it's pretty straightforward to generate a homogeneous Poisson point process because all I have to do is just grab a whole bunch of random exponentially distributed numbers, let's say increments like minutes or hours or whatever, that are have a rate of 1 over lambda, and then I just like add them up like some sort of cumulative sum of those things, and then now I have a whole bunch of events, right? I have one event at 5 minutes, and another event at 7 minutes, and another event at 8 minutes, and another event at 15 minutes, and so on and so forth, right? And so when you do that, it looks like this, which should look like noise, which is good. So that is a homogeneous Poisson point process. This right here, if it's noise, that is basically your, as long as it's binned correctly, this is basically your lambda here. So if I had said lambda is equal to 500, which I think I did for this, it's centered around 500, right? A non-homogeneous Poisson process is something that allows lambda to change with time. And so this is how the real world actually works. There aren't actually bus arrivals that are exactly 5 minutes. There are 5 minutes during rush hour, but overnight they're like 20 minutes, and different times of day they have different values, right? And that's can be computationally difficult to actually calculate how that works, or you can apparently, and this is like, I guess, the right way to do it, but you just cheat and you say, if this is what the curve kind of looks like for how this is really frequent, this is really infrequent, 0 means 0. Let's pretend this said 1 up here, okay? If I were to generate a homogeneous Poisson point process, let's say with lambda equals 500, wherever this p here, which is like some sort of probability curve that I define, which is the shape of of how the arrivals change with time. Wherever it's equal to 1, that's like instantaneously the arrival time is 500 a rate of 500, right? Whereas if it were 0, then I should get no events, right? And all you do then is you generate a homogeneous Poisson-point process and you just screen it by this number here, right? You have all your events that happen in this kind of bin right here, and you just say, well, what are the odds that that event actually happened? Well, you just generate random numbers and you say, oh, it's like 2%, and then you end up throwing away a whole bunch of those events there. And so what you do is you just generate thousands and thousands and thousands of events, you come up with some little function here, and then you just throw away a bunch of those events. And now you have a non-homogeneous Poisson-point process. So this would be an example of like that sort of probability function here. I have it saying that Monday, Tuesday, Wednesday, Thursday are all some sort of same number. Friday's a little bit lower. Saturday and Sunday are both way lower. So I'm going to like model transactions and say that, like, much like Spot Hero, let's say that these are people parking their cars and we don't have as much traffic on the weekends, right? Overnight is all these dips down here. During the day is all those dips there, and so that's just kind of sinusoidal. And overall, there's like this trend of it growing with time because Spot Hero is doing a good job. If it were going like this, it would be even better, but you know, that's all right. So you can take these numbers, this right here, put it on top of your Poisson, your homogeneous process, and generate this, right? So this is actually generated off of that same distribution before, which is not that one, which is centered around 500. A bunch of them ended up getting, you know, filtered out because of like overnight and everything else like that. And if I were to group them by, let's say, hour, it looks like, I would get something like this. And so on average, maybe about 200 events over here, and it kind of grows over time, right? So just to see what that looks like real quick, which is not necessarily necessary, but I have, first of all, this is way too small to see, but my name is Drew Fuston, and that's me everywhere. So github.com/Drew Fuston is my account. I have a whole bunch of repos on there. Talks, sort of double underscore is everything. So you can find any talk I have. This one's called Time Series Experiments. So it's just called talks __ Time Series Experiments, and you can find all this jazz in here. This has IPython notebooks in here. It has an environment that you could build. This is actually not correct. I copied that from somewhere else. And then it has like slides, so these slides and everything else, right? So, so that is that. And here is one of those notebooks. You could generate a homogeneous Poisson-point process. As I said, you just transaction times are just a cumulative sum of a random distribution, or a random sample from exponentially distributed of 1 over lambda. I want, I don't know, n of them, let's say 10,000. Unit D meaning days, I guess. I mean, that is what that means. And then you just add all these together, right? And so now I have a whole bunch of transaction times. If I wanted to be sure that that kind of looks Poisson, I would hope that if I take those transactions and I take the mean and the variance of those, that they should both be equal to lambda, whatever I choose. And then let's generate this thing. I want 50,000 events, 500 lambda, starting here, frequency 1 day, blah, blah, blah. Here are those events. There's one at 4 minutes, at 4 minutes and 21 seconds, at 8 minutes and 19 seconds, and so on and so forth. And yes, the mean is 501, the variance is 430. If I were to make n larger, that does in fact converge to 500. And just to check that that looks right, I could also just sample from a Poisson with 500 and get the same sort of deal, and it does look the same. The only reason I didn't want to do that is because I actually want, in this particular case, individual events, right? Because I want to eventually go into those individual events and say, no, I don't want you, yes, I want you, no, I don't want you, and so on and so forth, right? So that's the reason I did the exponential sampling instead of the Poisson sampling. And so then you define some sort of thinning function, which looks like a trend, looks like this, power law of something something. Cyclical looks like a sine. Nope, seasonal looks like a sine. Cyclical is just like a lookup table saying Monday is 1, Tuesday is 1, Wednesday is 1, Thursday is 1, Friday is 0.8 or something like that. And then I just pass this into that as a bunch of components. It makes this little curve, and then you can generate a non-homogeneous Poisson process by just basically calling a homogeneous point process, taking the thinning components that are that curve, and then just thinning it out, and sure enough, you get this little guy here, right? So now I have my sample data. I actually don't know if I have this non-homogeneous point process. Nope. So I don't want to actually go through here, but I would basically just have a pandas series, which is just a bunch of timestamps grouped by day, and it's how many events I have per day, right? So that is that. Let's go back here now. Let's go here. Let's wait for that. And ARIMA. Okay, so let's talk about forecasting real quick. As I said earlier, this is what like Wikipedia and so forth look like for ARIMA. I completely glaze over when I see this. I really don't want to because I really like linear algebra. It's just that for whatever reason this looks confusing, and I'm like I don't understand what you mean by delta is a drift, delta over 1. I don't understand what these things mean exactly. And so this has always been kind of convoluted to me, and I've never put enough time into it for it to be like second nature. So this is sort of how I react to ARIMA's. I love looking at Giphy, and I'm like, oh, I want to find something like existential crisis or something. And you find these, oh, so good. Good news, it's actually not super complicated. It still looks complicated, but it's not so hard. There's autoregressive, there's integrated, there's, oh, these two are flipped. I'll fix these notes later, but that should be like that. So autoregressive, basically, what it means is that, boy, I'm missing all sorts of stuff here. Let's go to the next thing. Well, I will explain it in a second, but I want to look real quick. There's that guy again. I love him. Okay, so you can actually see here, and I know, but hey, that you have 1 minus phi goes up to the p power. So this is, ARIMA is PDQ, so this is your autoregressive term, and it basically means 1 minus some number phi, let's say, times what's called a lag operator. I have it just called b in the other slides here, so it's just like 1 minus phi times b, right? If I take 1 minus phi times b, and let's ignore this, let's say that d is equal to 0 here, so this is just 1. 1 minus phi times b on xt here, xt times 1 is xt, minus phi times the lag operator on t would produce x of t minus phi x of t minus 1. Right? So that's what that lag operator does. Is all it does is just say, hey, this term here goes through all of these operators, and what happens over on the other side is x of t minus phi x of t minus 1. Right? So if I had higher orders, let's look at this guy again. If I had higher orders, you have phi 1, you have phi 2, and then that's b squared, or lag operator squared, all the way up to phi p, b, p. Lag operator squared means if I hit on xt, that means xt minus 2, xt minus 3, xt minus 4, and so on and so forth, right? The moving average, which is this one, not that one, is the same deal, except for it has different parameters in my copy off of Wikipedia, this is actually 1 plus instead of 1 minus, but that's all right. Same deal, except for on this term right here is the noise term, which is actually what usually ends up confusing me. But it just means, in this case, this is epsilon t plus theta epsilon t minus 1, right? And so eventually you can actually like walk through this whole thing and say, well, what is epsilon 0? Well, epsilon 0 is, I don't know, some sort of initial kernel, some sort of seed that I guess. And then what if I wanted to know what epsilon 1 was, I actually maybe now have an equation that I could solve. I have epsilon 1 plus theta epsilon 0 is equal to, let's ignore this term here, x of t minus phi x of t minus 1. And that's literally just an equation, right? That's not so hard. And then you do that for all sorts of, all the data points you possibly can, and then you can actually fit on what that theta is and what that phi is, right? So an example would be, and then moving average is literally just take 1 minus b to the dth power. 1 minus b, if this operated on x of t, it would just be x of t minus 1, which is literally just what's the step between t minus 1 and t, right? So that's all this guy does. Really easy to do in pandas. You could just like say whatever dot diff, and that'll do like that'll do the first order. You could do dot diff 2, and that'll do the second order, and so on. So an example of an ARIMA 110 model literally would just look like this. You would have 1 minus phi 1b minus 1b. And that is over on the left side. We can actually see what that operates on in a minute, but this is literally just the left-hand ARIMA operator here. If I were to just do my normal distribution, whatever that's called, I don't remember math anymore, but it's called, it results in 1 minus 1 plus phi, b plus phi, b squared, right? And so that right there is this operator, which hits, this is the awesome one, which hits right here. So I have whatever I just said times x of t. So I would have an x of t minus 1, an x of t minus 2 component on the left side. And if it was just a 1, 1, 0 model, that means that q is 0 here, which means that this goes away. And so this is literally on this side just equals the noise. And now I have an equation that I could solve and I could fit and find what those parameters phi and phi is. You know, that's all there is to it. So that's decently straightforward, actually, in my mind. You can even, in fact, add seasonal parts to it, because usually when you do like a non-seasonal ARIMA, you have to have like consecutive lags, and so you have 1 minus phi b, and then I would have minus phi 2 b2 squared, minus phi 3 b cubed, so on and so forth. But suppose I didn't want to have phi or b2 and b3 in there, right? I can have a different term here, which is your seasonal ARIMA, which maybe has, in this particular case, it says 1, 1, 1, 4 here. That means that the season is 4, which means that it starts at 4, right? And if I were to have a 2 here, then I would have 1 minus capital phi 1 b4 minus capital phi 2 b8, and so on, right? So you have that. Yes, this is ugly, but you could easily just work out exactly what this equation is, right? And it ends up being, ultimately you can have things upwards of 10th order lags, I think, here, because if I take b times b4, that's actually the b5, right? Because this literally, you can think of it not only as like a lag operator, but it actually works multiplicatively like you would think, right? So b times b to the 4th is b to the 5th, times b to the 4th is b to the 10th, right? So I would have at least one term, well, I would have exactly one term in here that would be b to the 10th, yt, and other sorts of terms, right? And so I'd have like yt minus 10 as well as a bunch of other terms here. And over here on this side, I would similarly maybe have like a epsilon t minus 5 or something like that, right? But at the end of the day, this is literally just an equation, right? And it actually, this particular formulation, really, really clicked for me. I don't know if it did for anybody else, but this right here makes the whole world of sense. So good job, ARIMA Forecasting. There are other topics that I'm not going to discuss just because of time. But there's all sorts of stuff with ARIMAs and gotchas and everything else. Checking for stationarity, meaning like, is my time series sort of wandering in time, or is the variance of my time series wandering in time? Like it's small now, but over time it gets bigger. That's not good. There's something called an adjusted Dickey-Fuller test that tests for that. There are these magic plots that are ACF and PACF plots. I'm sure if you've done time series stuff, you've seen them before, but they kind of look like this, and they have just their little histograms look like that, and they have these bars on them, and you say, oh, that one's significant, that one's not, and so on and so forth. And you just keep changing the PDs and Qs until you don't have any significant numbers anymore. Actually, I've got a pretty good idea of how you actually go about getting rid of all those things, which is really great. If something that actually has to do with the memory differences. If something is autoregressive, it kind of remembers things for a long time, and so like today's term goes as yesterday's term times phi, but yesterday's term times phi goes as the day before its term times phi, and so today's term goes as 2 days ago times phi squared, and so on and so forth. And so if phi is some small number, the amount of information I have from like the 10th and 12th and 15th lag or whatever just kind of approaches 0, right? And so one of these like ACF tests would actually, you'd have a whole bunch of lines that are like this, but they're getting smaller in time, right? Whereas moving average, literally it only remembers the last step, okay? And integrated is different. So let's talk about forecasting for a minute now. Over here in forecasting land, as I said, I didn't want to just stick with using built-in ARIMA stuff, but I did in the initial case at least. You have stats models here. Stats models has a ARIMA package in it. Now, finally, they have a seasonal ARIMA model actually in the sort of master build of stats models, which is great because it wasn't out there for a while. Also, the guy that writes this is over at Cibis, if anybody's listening to this. So here is a time series. That's my random simulated data, right? There's no steps here. So you could imagine if I were to run some sort of time series experiment, if I were to start it right here, I might actually see something here. It's like, oh my god. And this is what those weird autocorrelation, partial autocorrelation curves look like, right? And so this is the tea leaves that you want to, this is bad. You want all these dots here, all these histograms to be inside of the blue bars here, so that's not good. So what you can test for stationarity, which means is this thing drifting. I'll bet you can tell that thing is drifting over time. Sure enough, this number right here means not at all have I rejected a drift. This number this is a p-value, so if that number were less than 0.05, and it would be statistically significant, which is not true, but so that's how you use one of those things. So one thing you could do to get rid of that drift is you take the differences, right? So we talk about that integrated operator, which is just 1 minus b, right? So all that means is literally I just take my transactions diff, and now I have this new term here, whereas before I had transactions, they look like this. Now I have delta transactions, which is just this number minus this number, and this number minus that number, and so on and so forth. And those tend to look pretty noisy, and that looks a lot better. If you were to use the adjusted Dickey-Fuller on delta transactions, you would see that yes, in fact, those are, I can't tell the difference between this and white noise, so that looks good to me. Not white noise. I can't tell the difference between this and basically what you want. Can't remember what it is. So let's find a Sarimax. Sounds like a villain from Lord of the Rings. It is, in fact, seasonal ARIMA with exogenous something, I don't know what it means. But you give it your time series, you pass it an order, and how do I choose this order? I don't know, tea leaves. So let's guess 0, 1, 1. I do know that this thing is pretty seasonal, meaning, and my season means weekly in this case. So 7 lags backwards in time, I definitely want to have in there, and I'll just add a couple ones there to see what that does. You can see that there's a 7 there if you look back up here. This right here kind of dictates to you. This right here is 7. That number being really high is pretty indicative of you're going to need a seasonal sort of correction. Same thing here, you just can't see it as much. So you get rid of that little guy, and you throw this at it, and it comes back with some pretty good looking numbers. How do you know they're good looking numbers? I don't know. You try other things and you look at this AIC. AIC is a sort of goodness of fit thing that punishes you for being too good, right? So if I made this like 15, 7, 6, like it would really hurt, and my AIC would start to go up, right? And so I want to pick my minimum AIC. That's all that's doing. So it basically says the simplest model is the best. And look at that. That looks like kind of like white noise. And my God, that's just beautiful. This is what you want to see. There's not really a lot going on here. I'm pretty happy with those being a good forecast. And then you throw that thing out there. Turns out what comes out of stats models, you can grab this get predictions thing and you can give it like a dynamic start thing, which I thought was really neat. I did not know that this was a thing, but you could basically say, sure, I have this whole time series here, but I want you to ignore that you know anything about that time series from this time on, right? So fit it on everything beforehand, and then from here on, my autoregressive term for my like first forecast is based on today's number, but like my second one is based on a forecast, and my third one is based on a forecast and a forecast, and so on and so forth. So the numbers start getting much, much worse, which is why forecasts don't work over a long period of time. And this is a pretty stable time series, but you can see the blue is the actual time series, the green is my fit. I got some gripes with this myself, but we can talk about that in a minute. And then this gray here, which you can't exactly see, but the gray you can kind of see is spreading out over time, right? This, how it is starting to run away from the green here, that's just because blue is actually based on like an exponential growth, but it kind of locally looks linear, and so it's fitting it linear, right? And as I go farther and farther out in time, I'm gonna always kind of miss that sort of exponential part, and it's gonna, it's not gonna be good. So the other thing is like, man, I'm really, really missing like my weekdays, right? Because the peaks are always the weekdays. I'm really missing those. After the fact, I should have been doing some other sorts of transformations, like a box-Cox transformation, which is something you would apply to a non-normally distributed time series. This is definitely non-normally distributed because it is Poisson distributed. So it kind of transfers it into, or translates it down into sort of a normally distributed time series, which is what you want. So anyhow, this is what this would look like. You can imagine that if I would have started like a time series here, that maybe I would think that something was going on out there or whatever. But ultimately, here's your time series, here's your forecast, here's some numbers, right? Okay. And now is when I ran out of time. Also, I'm going to add a slide. So I had the flu over the weekend, so I lost like a whole day of writing this thing. So kind of ran out of time at the end, but I have the notebooks really well. I just don't have it all sort of written up here. Okay. So I'm going to use PyMC3 because it's cool. So PyMC3 is a Monte Carlo, it's used for like Markov chain Monte Carlo simulations. It's big in the whole Bayesian world of doing simulations to try to get fits of things. It's unfortunately based on like Theano as a backend, which is no more. So those guys are figuring out which backend they're going to use. I was just at the PyData conference in New York this past week, and holy crap, PyMC3 is like the hotness right now. So part of that is because it's like a PyMC or a PyData project, you know. So Stan is also a thing that exists, but it's kind of like for the R people. So if you're a Python person, this is core Python. It is beautiful, and it's, oh my god, it's so easy to use. I was trying to do some MCMC stuff a couple of years ago, and all the packages were out there. I could not figure out what was happening. This is pretty straightforward, which is beautiful. So, so I'm going to generate some random data. I'm going to fit an ARIMA to it just to get an idea of what my orders are here. I'm going to keep those in mind, because I'm going to then use then I'm going to add some sort of noise term to it, like basically some sort of, I have my time series, it's 500, 520, 540, 514, blah, blah, blah. And I'm going to apply to it some number, let's say a 20% bump, or a 10% bump, or something like that, at a very specific time. Okay, so I'm just going to go here, and now, boom, here's my event that happened. Okay, so that's how I'm going to simulate the event. I'll show you in a minute what that means. And then I'm going to use these ARIMA operators that we just went through and use PyMC3 and actually just kind of fit like you would normally fit things, as opposed to like trying to throw like an ARIMA thing at it. I'm going to like kind of hard code what the ARIMA model is into PyMC3, which I would never have been able to do like 5 days ago. So that's cool. And then we iteratively solve for y and epsilon. And I have other next steps that I want to kind of look at. So let me look at this last notebook real quick. How am I doing on time? It kind of seems bad. It's about an hour right now, which is long.
We got till 8. So.
All right. I will speed through real quick. So I have this non-homogeneous Poisson process that I generate. Looks like, yeah. I actually, instead of having it like very daily, I'm going to have it very weekly, just because varying it daily means I have to get seasonal, and doing seasonal and all of, you saw how complicated that like those operators were, and I was starting to do that today, and I was like running out of time, and I didn't want to do like a 15th order polynomial, so I didn't. And I'm going to add like a 20% effect size at some sort of time period in my time series. So my response just looks like, this is just a complicated way of saying it's what my time series was before treatment start, and it's what my time series was plus a number between, like a number around 0.2. So it's like 1.2 times what it was after the time period, right? And it looks just like this, right? So here's your time series, and then boom, there's your, right? So I should be able to detect that. That would be pretty nice, right? So then, as I said, I just take my just normal time series, not the one with the response in it, just the normal time series, the original one. And because it's not seasonal, and that's because it was too complicated, and I picked these particular 111 here just because they happen to work nicely, as you see here. That's pretty good. It's really good. That's also because there's not a lot of noise in my time series, so it should fit really well. And then I am putting everything into a data frame just so it's convenient for later use. So, as I said, here's your transactions, and this is what I'm going to attempt to detect here. Okay? So, here we go. Here's PyMC3. I just have some like little scribbled notes here as I was trying to work through things. But I'm going to use a 111 model, and I just wanted to keep in mind that was phi and that one was theta. In Theano, oh, I forgot I left that in there. That needs to go away. That's right. Oh no, that's okay. That's So what you do with PyMC3, sorry, is you create a model. So PyMC3 as PM, right? You build a little model guy, and I'm going to call it ARIMA model, and then you like specify all sorts of different little variables that would be part of my model, let's say. And because this is Bayesian world, you initialize them with some choice of an initial sort of prior assumption, right? So I have mu, which is like my actual like mean of the time series. You have sigma, which is the actual noise on the time series. And you have phi, theta, and this beta term, which I will talk about in a second here. And these are all just kind of, these ones are all normally distributed. Noise should not be negative, so it's half Cauchy. And then, turns out, and I'm not 100% sure I used this right, that Theano has this thing called, so Theano is like a way of dealing with tensors, and I'm not quite there yet with all the tensors and stuff. Like I can't like look at them like I could like a numpy, I call it numpy by the way, array. But basically what this is, this switch thing here, is it's like, hey, if you give me some tensors, I can do stuff with that. And if this first part evaluates to true, then do the first thing. And if not, do the second thing, right? It's like your Excel like if function, but for tensors. So I say it's y if I'm before my treatment start, and it's y minus this effect size that I have added on, right? And this here is what I'm going to attempt to back into. Like, what is beta? Like, is beta greater than 0? Is beta less than 0? Blah blah blah, right? But the problem is I also am going to be solving for phi and lambda and theta and so forth. So it's not like I can just like say phi is this and theta is this and therefore find beta. It solves them all sort of at once, and it solves them all probabilistically, and so it kind of gives you a whole range of values that could be true. So here's my scratch notes walking through those operators. If this is a 1-1-1 model, 1 minus phi b times 1 minus b. So that's your p and that's your d, right? Times yt is equal to 1 plus theta b epsilon t. So just expanding these things out looks like that. Bringing this epsilon t over to this side and moving everything else to the other side, you end up with the current noise, the noise of the current step, and I'll explain what I mean by that in a minute. The noise of the current step is equal to the value of the current time series position minus yesterday's time series position, or last week's I guess, minus phi times yesterday's plus phi times 2 days ago minus theta times yesterday's noise, right? But I know this, I know this, I know this, I know this by the time I've gotten to calculating this, right? And so these are literally just numbers at this point in time, because like this is a time series, right? And I'm now at t equals, the switch plus 5, right? So I know what it was at minus 4 and minus 3 and so forth, right? I was following some other sort of thing. They called something new, which is just the difference between this y and epsilon here. I don't know why they did, but this is what they're going to end up writing a function for here. So epsilon 0, what is my initial value of epsilon 0? Because the problem is if I'm trying to evaluate epsilon at 1, I need to know epsilon at 0, right? But I don't know what epsilon at 0 was because there is no 0. And so if you actually just like work this through, what is epsilon 0? Just put 0 in here and then calculate the expectation value of the right-hand side. The expectation value of y0 is mu. Expectation value of y t minus negative 1, also mu. So those cancel. Same deal here, same deal there. Those cancel. So, Oh no, sorry. Y0 is actually a number, right? So Y0 minus mu, and the rest of this cancels. Because the expectation value of epsilon is 0. So epsilon 0 is equal to this. Okay? So that's my initial guess. I know what this value is. What's my uncertainty? Well, that. And look at that. That looks pretty correct, actually. It's mu, which is the mean, and my observation. So now I just create this function that I can walk through and say, because I need 2 lag, 1 lag in today's y, and I need epsilon, I need mu, phi, and theta. This right here is just me writing down this equation right here. Okay? And I am going to then, and I don't know what the hell this is doing, but I copied it. So, but I do know that it takes this tensor, and I guess if you give it taps -2, -1, 0, that gives me those positions that are 2 steps and 1 step behind. All right. And this is kind of like my initial seed, I guess, and then these are some other numbers that it's going to fit. And this scan, I don't know, again, what it does, gives you epsilon, such that I could then say that this thing is normally distributed, whatever, and that will return an ARIMA model. And then if you build this model like so, it'll produce a trace. And what a trace is like, I say I want 2,000, so it's going to give me 2,000 opportunities of fitting this thing. And what I could do with those 2,000 sort of traces, I could figure out well, what's my spread in mu, and what's my spread in theta, and so on and so forth. So you do this trace plot thing, and it looks beautiful. This is good when one of these MCMC calculations converges. It just looks like noise here. You might see in other sorts of packages that it'll converge to a noise and then it'll stay there. But regardless, if it's just bouncing around, that's solid. These actually look pretty solid to me. I'm not 100%. This is with some sort of translation on the time series. I'm not entirely sure what the definition of mu is here. But phi and theta are what they think they are what they should be. And so if I look up at what my actual fit for phi and theta were, my phi was -0.5, and my theta was -0.15. That looks pretty dang good, right? But I now have a whole bunch of uncertainty around that number 2, right? So that's actually good if you're me. And you've got theta as well, and then you look down here at beta. This is your effect size that I was trying to fit here, and look, that's 0.2, right? And so if somebody were to say, hey, what is the effect size? I would say, well, it's a 95% confidence, and you just find out what those boundaries are that give you 95% of this curve, and you would say it's 0.12 to 0.28 or something like that. And as I have more and more observations in the future, I can now get beta more and more correct, right? And no way would I have had any idea how to do this prior to actually figuring out how ARIMAs sort of decompose into a thing. The next step I kind of wanted to do, which I'm not going to do right now, was to actually look at fitting a line using MCMC3, or not even a line, but yeah, a line I think, like this. But then also looking at what the line fit afterwards would be, and then say, well, this has a slope and a y-intercept of these values. This curve here would have slope and a y-intercept of some other crazy values. Maybe if I were, only gave it 5 numbers or something, it would look like this, which looks terrible. But if I were to, and I don't know if this means anything, but if I were to plot these 2 distributions, if there was no change, these things should probably be overlapping on top of each other, I think. And so I'm fairly certain that with 5 observations, 5 daily observations, I can tell that no, these 2 are not the same distribution, right? Which is cool. I'm sure I could figure out what the effect size was and everything else, but I'm certain looking at that those are not the same distribution, right? So I want to dig into that more too, but I ran out of time to do that. So yeah. So yeah, that's that. That's the talk. Thank you. Do anybody have questions? I'm sorry I went over. I never timed these things right. Yeah.
So that was really great. And I like how you're just kind of getting into what you would look at next with each of these. What would you look at next now?
I mean, I want to look at this because I want to figure out if I could do something with this. I don't, as I said, I don't know what this is doing enough that I'm comfortable with it. I like went to a few PyMC3 talks. I was like, oh god, I got this. This is amazing. Like one of the contributors for PyMC3 was he built a model for his like commute, and he said like, well, you know, the average time of the train is this, but sometimes the train is late, and if it's late, then I could give it a different like seed, like but if it's late, then I might actually take when I get downtown, I might not take the bus, but I might grab a bike, you know. And now all of a sudden you have this like parameter that is like, do I take a bike or do I, you know, whatever. And the way he built it was just so intuitive. It was like, oh my god, I understand this well. And then I tried to do it, and I was like, oh, I don't get it. So I want to spend a lot more time with PyMC3 because it's just beautiful. Because like literally you build like a model like so, and then you just kind of see what it does, you know, and you hope it converges, and you feed it some data, and it kind of does its thing, which is amazing. So, and it's, I know this kind of maybe doesn't look necessarily intuitive, but the more you sort of play with it, you're like, this is beautiful. So, so yeah, that's the other thing I want to do is just figure out what the heck I'm doing. Yeah.
I guess I was kind of, well, first off, thanks for presenting. There's a lot of good stuff there. I guess I was kind of looking for more, like, here's my interaction. How do I know if it actually made a difference, or it was due to chance, or due to variables that I didn't include in my model?
Right, right. Yeah, that's another thing I actually want to do. For one, here's my interaction. If beta were as large as 20, you know, 20% or whatever, then like I would know that something was up, right? But I would kind of, what I would want to do with this is like back test it and like historically test it and say like, what are the odds of something like this happening by random chance without there being some sort of like weird control thing, right? So that's another sort of thing that I would want to do with this as well, is make it such that this is just like a little function. You pass it a t and you pass it a beta, and it just does its thing. And then you just run it over all time and kind of see like how likely it is for these different things to happen. And the other thing I wanted to do was, when can I stop and know that yeah, that thing is past like sort of criticality, right? I made it weekly, and this made it such that I have to wait like a month or something, which is way too long. I should be able to figure this out in like a matter of days or whatever, right? So if that's the case, like, how do I rewrite this in such a way that like, oh, day one, beta is somewhere between -1 and +2, and you're like, well, that's not helpful. Day two, it's like in between -0.5 and +1.5, you know, and then it slowly zeroes in to the point where I'm like, no, that is definitely a positive thing. I know that this thing succeeded. If I wanted to know exactly what the number is, I could let the experiment go on longer, but I know it's at least a good experiment, or vice versa, I know it's a bad experiment and turn it off. That's the other thing I wanted to do. Yes?
There's this package in R called causal impact. It's
Mhm.
from Google.
Oh, yeah.
It's like Bayesian structural time series, and basically it like breaks down your time series and says, well, if we're going to try and guess like what should have happened if no change was made. Like we have the data where the change was made. We're going to guess what should have happened, and we're going to compare the differences and kind of guess what the impact was.
Yep. I mean, that's ultimately what this is doing too, because that's what the phi and the theta are here.
Yeah, exactly.
And so like, beta 0 is nothing happened. Yeah. Beta not 0 is something happened, and that's like the thing you're kind of trying to
get. Yeah, that's what I was gonna say. That's what this reminds me of.
Yeah.
It'd just be, I think, nice if there was an equivalent in Python.
And there may be. I might be reinventing the wheel. I do it all the time. But given that, I mean, like, seasonal ARIMA wasn't even like available in like general Python land until like the last year, which is crazy to me. Yeah, there were some also causality things I wanted to try to figure out too, because there's like some test statistics and stuff to look at causality, and I've never explored those before. So that was the other thing I kind of was looking at doing too. I was basically just pinging my friend who's like a quant trader who's like the smartest person I know, and was talking to him about this. He's like, oh, you should look at this, and you should look at that, and you should look at this.
Yeah.
So,
I went to like a finance conference back in the day. This is like all the time on this time series.
yeah, oh, of course. I mean, that's money right there. I just made money, you know. So yeah, and I'm a rookie. I don't know what I'm doing. I'm like doing, you know, like marketing radio spend, you know. So yeah.
Have you ever tried like other non-linear models, like non-linear machine learning models on time series and seen how effective they've been?
Yeah, I mean, the other thing is like, why the heck ARIMA? Why am I sticking myself to like because ARIMA sort of requires that your noise is Gaussian distributed. So that's why like I had those like, it was going off the rails and the tops and the bottoms. I know better now, but I ran past it somehow. You could do, there's all sorts of methods, right? And there's different Bayesian methods as well from scratch that are Bayesian, like the whole time series thing is Bayesian. Why I mixed ARIMA with some other Bayesian framework is just because ARIMA clicked with me and I was like, okay, let's just run this through PyMC3. But like, yeah, same deal, right?
Yeah.
You should be able to do the same deal. There's like VAR, which is like variant autoregressive or something like that. What's it called? Vector autoregressive. Whole winners is another one. Yeah. So.
I mean, that's one of the beauties of the PyMC3 is you can write the equation, you can run the Bayesian estimates.
Yeah.
I think one thing that could be cool, kind of combining these two ideas of what you're doing here, kind of analyzing with the generated data and what you're talking about, it's like, here's the actual experiment, how do I know, is I wonder if you could take something like historical data, do a fit to the historical data, and literally add in to that historical data some amount of impact and assess how long do I have to run my experiment if my impact effect size is 20%, 5%, 1%, and see that the necessary time to get significance is going to get longer. And that might be a way to prepare an experiment before you even do it. And you can try it at different time intervals. And
Oh, just because your transaction rate is higher now than it used to be, and so now it only takes 2 days, whereas it used to take a week or whatever.
Yeah, and just as a kind of a preliminary to look at the cost of experiment versus the probability of seeing the results, because I mean, like what you were saying with assessing how much longer you're going to need in order to determine, getting that window even before you've done the experiment.
Yeah.
Hey, this is how much this experiment's going to cost, guys.
Yeah, and this made me like sad that I had to like go so long to before, you know, I could get beta. Well, I was actually trying to like toy with passing it, not the whole response series, but only the response series plus like 5 steps beyond like the, you know, the cutoff time, and it was just like beta was 0, you know, statistically 0, and that was just disheartening. So, but this looks like there's no way that's true, you know. So I think there's more there.
Did you compare the PyMC predictions of the baseline pattern to the stats model's prediction?
Yeah.
Were they basically the same? Did it still have that underfitting of your weekdays? Sorry, the actual prediction curve.
No, I actually didn't plot it. No, I did not.
I mean, I guess you'd have to generate it.
Oh yeah, but it's cool. I want to find this other guy's talk real quick, just to show you how beautiful. So this is his sort of, he built a model which is train time takes bike time, walk time, time to train, or time T, I don't know what that means, total time. And so he has this like switch in there, like, does he take his bike? Because if he does, then it's bike time. Otherwise, it's walk time plus T time and blah, blah, blah. And ends up like figuring out that like this is the distribution of his arrival times at work. But like, oh, my train is on time, so now update you know, what your expected arrival time is now, instead of it being this, it's now that, and it's just awesome that you could like, train's 10 minutes late, oh now the distribution looks like that. It's just amazing, and it's this many lines of code. I mean, like no, that was a lot of that. Most of that's plotting. It's like this many lines of code, and then you feed it like, you just say train time is equal to 40, and then it, you know, yeah, it's incredible. But the thing I was going to go in with was like this sort of deal where if you're trying to fit like some sort of polynomial or whatever, you can actually, you know, just fit all sorts of lines to it, you know, and you can actually see what the lines are doing, and you can actually see that they're going through here. So he like went through this whole thing where, oh, let's look at Bayesian ridge regression in PyMC3, and let's look at lasso regression in PyMC3, and like look how well it does, you know, like there's a bunch of outlier data right here, and it would be real easy to fit that data incorrectly, but it like just doesn't, which is really amazing. I mean, it kind of does, but that's pretty dang good. But yeah, so draw all those lines there, you know, and that would basically be your forecasts, you know. That's basically what I would do. Thanks.
Any more questions? Well,
Cool.
Thank you very much, Drew.
Thank you.